Hello friends, welcome to the video lecture series on analog communication. My name is Rajnaran Shriwas and today we are going to learn signal to noise ratio. So let's start. So let's define signal to noise ratio. Signal to noise ratio is a power ratio which is abbreviated as SNR. Since this is a ratio of two same things, so hence it is a unitless quantity. Now, if you see mathematically, at any point, signal to noise ratio can be defined as the ratio of signal power to the noise power. Here we are using PS to denote signal power and P sub n to denote noise power. Now, at any point in a circuit, if you know the voltage or current of signal and noise, then you can write this signal power and this noise power in terms of signal voltage and the noise voltage, similarly signal current and the noise current. Suppose the signal voltage or RMS voltage of signal at that point is Vs and the RMS noise voltage at that point in the circuit is Vn, and the circuit is offering resistance R, then the signal power can be written as Vs square upon R. Similarly, Pn can be written as PVn square upon R. R and R got cancelled, so we get Vs upon Vn the whole square. So this signal to noise ratio, it is the power ratio, or you can say this is voltage squared ratio. One thing to be noted here, as I said, this Vs is the RMS signal voltage and Vn as RMS noise voltage. But if you take this signal voltage as a peak signal voltage and noise voltage as a peak noise voltage, then also the SNR will not change. It will give the same result, in other words. But do remember, whenever you are taking signal voltage as a RMS, so you have to take this noise voltage also in RMS. If you are taking this signal voltage in peak voltage, then you take this noise voltage also in peak voltage. And same for if you are taking peak to peak signal voltage, then you have to take peak to peak noise voltage. Now, sometimes signal to noise ratio is also measured in dB, that is decibel. And how to find SNR in decibel form? It is very simple to find that the SNR which we got as a ratio, you can take the log of that SNR ratio and multiply it with 10. So we call it what? Signal to noise ratio in decibel. So whenever you are given with signal to noise ratio in decibel, you can find SNR, and whenever you are having SNR as a ratio or as a factor form, so you can find SNR in decibel. Now let's see why this signal to noise ratio is so important. The measurement of signal to noise ratio is particularly important because we want to know the relative strength of signal with respect to the noise at any point, at any location in the system, right? So, if you see, the stronger the signal, then weaker the noise and higher the SNR value, and this is a desirable. If you see, if the signal is weaker and noise is higher, then this is going to decrease the SNR, and in that case the reproduced signal may not be a faithful reproduction of the original transmitted signal. So it is very important to have a minimum level of SNR to reproduce the original signal back, because noise is going to distort the signal. If it is more, then the distortion will be more. Now let's derive the SNR for a tandem or cascade connection. We want to see when more than one system connected in a series, then what should be the overall SNR for such system. So let's derive this expression of SNR by taking an example of analog telephone system. So if you see this analog telephone system, it consists of cables and the amplifiers at the regular interval of its path. Why we have to use repeaters in between? Because as the signal travels, it gets attenuated. And when the signal gets attenuated, so we have to boost the signal again. As the signal travels more and more, the attenuation becomes more and more. So we have to use amplifiers or repeaters in between the path. So as the signal travels, it gets attenuated along its path. So to make up this loss, we need to deploy amplifiers at the regular intervals along the path. So let's assume that a cable loss per section is L, that after a certain cable length, we are going to use an amplifier. So that cable length is called as one section. And suppose after traveling that section of cable, signal loss is L, then we need to use an amplifier whose gain is G, and we can choose this G such that L times G is equal to 1. Means there is no loss, no gain. Let's see this in a picture form. So this is cable section. So this is one cable section. We are talking about this is so this is one cable section, and after traveling this much length along the cable, the signal gets attenuated with the power loss L. So to make up this power loss, we have to use amplifier after this cable section whose gain G should be such that LG is equal to 1. So this is the cable section and this is amplifier section, and this gets repeated. So let's suppose there are M such links. So what is link? Link is nothing but one cable section plus one amplifier. We call this as a one link. So one link consists of one cable section and one amplifier. So let's illustrate this power flow in this system. If you see, we have assumed there is no input noise to this system. So noise at the input of this system is 0 basically. So there is no external input noise to this telephone cable system. And let's say there is a signal power at the input of this cable system, and the power of this signal is PSI. I stands for input to the cable. So PSI is the input signal power to the cascaded system. Now the signal, when it travels one section of cable, as I said, it got a power loss of L. So at this point, the signal power should be PSI times L, and the noise is still 0. because it's 0 time L and I will get 0. In any practical case, you can see this loss has to be lesser than 1. I hope this is clear, because this is the loss. Hence, when signal travels along along a path, it gets attenuated. Means the loss L is less than 1, right? So we have to use amplifier so that we can boost this power. So there is an amplifier which we deploy, or we call it a repeater, whose gain is G, and we choose G such that L into G is equal to 1. So after this amplifier, or you can say after each link, the signal power now becomes psi times L times G, and we said that L times G is equal to 1, so we get signal power as psi. If you see the external input noise, it is still 0, but there is a noise called as internal noise which is added by this amplifier. So this is a noise which is generated within this amplifier, and we can see this noise is appeared at the output of this amplifier. So PNA1, it stands for noise amplifier, that is amplifier noise, and 1 stands for, this is the first amplifier, so we are denoting it by PNA1. Let's see the second link. So if you see the second link, the input signal power is psi. So again we got a loss of L at this point, and then we got a gain of power G after this amplification. So again this psi gets multiplied with L, multiplied with G. So since Lg is equal to 1, so signal power remains the same. So you can see signal power does not change after each link. But let's see what happens to the noise. Now this PNA1 will work as an input noise to this second amplifier. So this PNA1 again gets multiplied with L and then multiply with G, and since Lg is equal to 1, we get PNA1, right? This is the noise which was present at the input of second amplifier. This is the internal noise which is added by this second amplifier, that is PNA2. Now you can comment that the noise gets accumulated after each link. These noises are basically the internal noises which are generated within the amplifier or within the amplification stage. So if you see the last stage, that is my mth stage, the signal power has to be, the input to this signal power has to be psi, because as I said, this is not going to change, but the input noise has to be all the internal noises from first amplifier up to the m-1th stage amplifier noise. So that is going to be PNA m-1. So there are m-1 internal noises for m-1 stage. So this will work as an input to this mth last stage or last link. So if you see, the signal power remains the same, that is output signal power, which is same as the input signal power. If you see the output noise power, it is going to be the all the internal noises of previous stages plus the internal noise of this current stage. So you can see the output noise power is PNA1 plus PNA2 up to PNAM. And if you see the input noise power, it is 0. So let's see the final result. This is the input signal power, and input noise power to the system is 0. If you see the output signal power is same as input signal power because there is no loss, no gain in each stage, and we get the same signal strength at the output, which is same as at the input. Now if you see this input noise power, here it is 0. So input noise power at this moment, it is 0, but the output noise power, it is the addition of all the internal noises of the amplifier stages. So if you see the signal to noise ratio at the output, it is going to be the ratio of output signal power to the output noise power, and this is output signal power, and this is my output noise power. So we got this expression, that is PSI upon PNA1 plus PNA2 up to PNAM. Now if we assume all the amplifiers are identical, then it means the internal noise of each amplifier is same, and let's assume that equal to PNA. In that case, what will happen to this expression? The numerator is PSI and the denominator, since we are adding M times the internal noise, so we should get that is M times P and A. So if you see, this output signal to noise ratio is nothing but input signal power divided by factor M multiply with internal noise of one amplifier if all the amplifiers are identical.